engineering renaturation of canalized rivers. 60 years ago, I was taught these things. No, not 6 years ago, but when I studied, we put a lot of rivers into a straight riverbed. Just why did we do it? The reason was to improve the navigability and to preserve land for agriculture. This is now a thing we wouldn't do anymore. What we are doing now is sometimes we put the river back to his old riverbed, just to get more possibilities to store water during heavy rainfall. A very important point is the zero energy building, the building construction, which is a big challenge also for the thermal insulation and the fire protection. And also we would like to use only renewable energy in the building. So it's very complicated to take all things into account. Renewable energy, of course, building wind turbines is a job which are the mechanical engineers doing together with the civil engineers. These structures are complicated also because of vibrations. I will come back to this a little bit later. And the last point I would like to introduce you here is the building restoration instead of demolition and rebuilding, which is also our subject. Here you see an old building. And instead of removing it, you have the opportunity, if you know how to do it, to restore it. And this is also a question of the fire protection and the thermal insulation, which is very important in this field. So now the introduction I just finished. We will now go to two special projects we worked here, or we are just working here in Wismar at the moment. The first one is a tuned fluid pellet damper. I will describe it in some minutes. And the third point is the maintenance of steel bridges. And finally, Natalie from Butler will conclude with the sustainability assessment of this concept. So now let's start with the tuned fluid damper. At least we have a lot of buildings who are usually influenced by dynamic loads, and we have to do something that they could do their job also when we have earthquakes or strong winds. So we need something like a vibration damper. And now, because vibration, that means I have to show a lot of videos, I have to change. First of all, let's talk about the functioning of a tuned mass damper. The best way to explain this is by looking at a bridge, and you see here a bridge. In the animation, you can see how the person wants to make the bridge vibrate. At first, he does not succeed because he has not yet reached the resonance frequency. But now, soon he has hit it at 2.0 hertz. He moves in sync with the bridge and the bridge resonates. If he now speeds up, he moves away from the resonance frequency and the oscillation amplitude becomes smaller again. As civil engineers, we naturally always want to avoid this so-called resonance vibration. The vibration can be caused by people, as in this case, but also by road and rail traffic, wind, earthquakes, bell vibrations in church towers and other dynamic loads. With the help of a vibration damper, the resonance vibration can be prevented, no matter what the excitation is. In a vertically vibrating system such as this one, for example, this is done by adding a spring and a so-called absorber mass at the point of the greatest deflection. An example in the middle of the bridge. If our person now tries his luck with the same frequency, stop, as before, nothing happens because the mass works antiphase to the bridge. We have reproduced the whole thing here as a model. You can see it now. In the first video, the small bridge vibrates in resonance. In the second one, this is prevented by the absorber mass. However, this is only half of the truth. Unfortunately, two new resonance frequencies are created above and below the old frequency. Oh, that was too fast. You can see it here in red. With both new frequencies. So we had no vibrations at the old frequency, but we have now two new problems. So we can switch further now. In animation, we show this by letting the person move slower at first and then faster and faster. You see now in the beginning, he is below the first new frequency, nothing happens. Now at 1.8 Hertz, he reaches the new lowest resonance frequency. However, the bridge and the absorber mass move in phase opposition to each other. I will come back to this later. If then increases the oscillation frequency to 2 Hertz, the bridge comes to rest because the absorber mass moves in exactly the opposite phase to the virtual person from below. When it speeds up and reaches 2.2 Hertz, now the second resonance vibration occurs. Here, too, the bridge and the absorber mass move inversely in phases. If he speeds up even more, the bridge and the absorber mass come to rest again. In summary, we can say that instead of 1 resonance frequency, we now have 2. So the problem has virtually doubled. And the diagram you see here illustrates this again. The blue curve shows the system. It's another system, another example. Without the mass damper, here's the resonance frequency at 2.8. Only when I excite it, I do get large oscillation amplitudes. With the mass damper, there are now new resonances at about 2.4 and 3.2 Hertz. It is important to bring damping now in the system because we have a relative movement. So if we put a viscous damper in between, we will solve the problem. I have to stop it. What we are doing now is that we will increase the damping. So you could see that the exact damping is very important. Yes. So now we have a very low damping, which is now increasing. So the amplitude in the new frequencies are going down. If we reach the optimum, which is now here, we have everywhere not a high deflection. But if we increase the damping a bit more, increasing the damping means we got a stiff connection between the tuned mass damper and the bridge. And then we, of course, get again the old frequency. Okay, and this is now the optimization we have to do. Here you see a typical tuned mass damper for bridges with a mass, for springs, and 2 dampers on the left and right side. However, these mass dampers do only work for vertical vibrating systems and not for systems you can see here, not for towers, not for skyscrapers, and not for elevators or lifts. They are vibrating in horizontal direction. Now we have reproduced these structures in model scale. In the first video, oh wait, I was a little bit too fast. So what can you do? You can then add a pendulum to the skyscraper, for example. This is one possibility. And this we have done here in model scale. You see here the structure without the pendulum, and you see on the right side now the pendulum with the structure with the pendulum. And very important is that the pendulum has to have the right length, so that it's just working with the same frequency than the structure. Okay. Now this is a problem with is that we now also need a lot of dampers. You can see it here for the skyscraper, and you can see it on the right for the wind power station. And even another problem is that if the structures are getting bigger and bigger, the frequency is going down, and so the pendulum is getting longer and longer. And it needs a lot of technique and a lot of space. So another possibility is the fluid damper, which you can see here. It works nearly in the same way. When it works in antiphase to the structure, the sloshing. It's quite a very intelligent solution. If the water is going to the right, you got more pressure on the right side, so the mass of the water will go to the left as it is doing with the spring. So, but again, we need a damping. That's a problem. No? We will have when we increase the frequency, we will get a new resonance frequency. So, wait, no, I have to stop a bit to tell you something. I have to go a little bit back. The thing is now, how to put damping in the structure. We have the water and we need damping in the water, and that's the problem. And this problem was solved by a female student. She was, when she had this idea, which is now a patented idea, she was in the second year of her studies. So this is very interesting. It's now 7 years ago, and since this time it's a research project of our university, and I can show you now how it works. First, you see here something like an earthquake. Exactly, it's not an earthquake, it's a basketball, but it will give an impact in the structure, and you can now see how long this structure will vibrate with a very low damping, because there's nothing inside, it's no water inside. So this is the baddest solution. If you put now water inside, you can see that it works a bit better, but not really good. You got another lower frequency, but it's again sloshing and sloshing and vibrating, also with a very low frequency. And the idea of the student was now to put some pellets on top of the water, and so you got a very fast reduction of the vibration. And the damping is 20 times higher than without the pellets. And to compare all these solutions, or all these models, you can see it here. You get the far best solution with water and pellets. And this is the same that you get when you go to the pub. You can see when you ask for a Guinness and for water that the foam on the beer makes the same effect than the pellets on the water. But the problem for us now in the research project is to find the right amount of pellets to get the right amount of damping. So we have here some experiments we did with water with different amounts of pellets. So you see that if you have a lot of pellets inside, you got a very high damping, and if you have only the water, it will slosh for some minutes. Now, this is quite a field where we can work on for a lot of, and it has, I told you before, it has a lot of advantages against the pendulum, because it is very a simple technique just to implement. And the damping, as you can see here, is going up when we increase the amount of pellets. Okay, now let's see what we can do with this technique. All structures, a large number of applications with very different resonance frequencies are visible. Usually they are vertical orientated, like the hangars of a bridge, or like the clock tower, or like the wind power stations, or like skyscrapers, also like a special type of bridges. So in case of wind turbines, we are thinking both of large offshore wind farms on the left and also smaller wind turbines like that one shown on the right. The shape of the tuned fluid damper has to be adapted to the tower. While wind turbines receive the stress from wind-induced transverse vibrations, for example, church towers on the right are excited by other impacts. In the case of the building on the right, it's the bell vibrations. On the left, it's a campanile in Italy. The vibrations follows the earthquake loads. In both cases, the space requirement of the fluid damper is not a major problem. There's enough space on top. The viaduct shown here under construction is very soft in the lateral direction and therefore vibrates horizontally at an extremely low frequency. A fluid damper could, for example, be placed inside the hollow box. The curves document the improved reduction of the free oscillation. Oh, I'm too fast. The curves document the improved reduction of the free oscillation behavior and almost complete elimination of the resonance frequency by the damper, as you can see in the red line on the bottom. In skyscrapers, the sloshing absorbers are usually placed in the upper floors. Land pricing are rising, consequently buildings becomes narrower, taller and slimmer. The frequency decreases and the pendulum have to become longer. More space is lost. A tuned fluid damper is orientated horizontally. For these reasons, these systems are currently experiencing a renaissance. For example, in the case of the Leonard 56 skyscraper in New York, you can see in the middle. However, the effectiveness with a suitable damping system is comparatively low. This is our laboratory engineer Kai-Henning Kruse. He will show us a new test rig we built here on the campus of the university to test the fluid dampers. a 10-meter high tower that you can make swing very easily with his hand. On top of it, we have erected a platform on which we can fine-tune the resonance frequency of the tower with additional weights. You can see in orange on the bottom. And mount further equipment for the test. You can already see that this tower can easily be set into oscillation. It's relatively easy to rock it up with his hand alone if you hit the resonance frequency. We mounted then later a vibration exciter on top of it that can set the tower vibrating with a defined mass and force. So we are now, later you see it, making we are looking for the resonance frequencies now. But first of all, we have to put the water and the pellets inside. It's still vibrating. It's vibrating for 2 or 3 or 4 minutes. Now the water is going inside, and also the pellets and some other things are not allowed to show because we didn't, for patental reason, we couldn't show you some secret things. So you will see that he is putting a box on top of it. And now we are just trying to get it into resonance, but with no success. The resonance frequency has completely been decreased and we have only small excitations. So the problem of the large oscillations is now solved, and that is only due to the water, the pellets, and the secret ingredient I couldn't talk about. Finally, we have now a few graphs of the experiment just shown. First, we made the tower swing and then stop the excitation. The first curve shows the free oscillations behavior of the tower head without the damper. After 40 seconds, the amplitude is just halved. With the fluid damper, the amplitude can be reduced to half after only a few seconds. You can see now. The evaluation shows that the damping factor could be increased to 20 times. And the last picture in blue shows the response spectrum, so the different frequencies, and with the blue line the red line shows that we eliminated the resonance frequency. So this tower is now well prepared for dynamic effects of any kind. Finally, we made another experiment just 2 days ago. We pulled the tower to the left with a rope, and then the rope abruptly was removed. You can see it first without the damper, just in a few seconds. You see that it's vibrating for a long time. We have not enough time to show you that it's vibrating for 4 minutes. And then with a tuned mass damper, we couldn't see very much vibrations. Just in a few seconds. So now we stop it. Now with the box and with the mass damper on it, you can see that it will be that the vibrations are stopping after some seconds. Okay, this was the first theme. Now we are changing to the second part. I think we will. Okay, we can make a small session during. I am changing back to my PowerPoint. Oh. So there's a question. I'm just looking what you asked. A multiple spring system of the roof of the bridge. Okay, I think it's a bit more complicated. Maybe we can talk about this later. I send you my email address, so I think it will take too much time. Maybe when we have some time at the end, we can discuss it. Okay, so I will continue with the second project we had. This is now a project about maintenance of steel bridges, but not of all kind of steel bridges, more the very old ones, therefore it's not the solution, you will see later. The both one on the left side are very old, older than 100 years, but the other ones on the right side are younger than 60 years, so they have a typical construction we called Autotopic steel bridge deck. And I have one here, not from steel, as you can see. It's from paper, so it is the typical way we are building steel bridges since 60 years. You have on top, you have a deck, a steel deck, then you have a hollow, you have closed stiffener, and then you have also cross beams. The cross beams you can see here. Ich muss die, sonst kann ich es nicht zeigen. Ist die andere Maus da? This is a cross beam. So, now let's look at an example. It's a highway bridge, Rader Insel in North Germany. It's now nearly 50 years old and 1.5 kilometers long. You can see here the autotopic deck with the hollow stiffener. Here, the hollow stiffener, and the cross beams here. So what is the problem? This is a drawing of the bridge, of the cross section of the bridge, and these hollow stiffeners are very narrow. They're not very wide. Here is one originally. It's only 300 millimeters high and wide. So that's a problem you will see later. Because of the dynamic loads and the fatigue, we have cracks in the welds, like shown here. So water can go inside, and water means not only water, it means also salt. Why salt? We put salt on the streets in winter because we have very low temperatures here, and we have ice on the bridge, so there's salt also in the air, and also if we are very close to the Baltic Sea, we have also some salts there. Salt and water inside means corrosion, and this is a result. In this case, in this bridge, we have now a reduction maximum from 6 millimeter to 3.8 millimeter. This is more than the third part, and this is statically a big problem. So one idea is to remove the bridge and build a new one. This we don't want to do, of course. So we thought about how to deal with it. So first of all, you have to look into the hollow stiffener, which is difficult because nobody can go inside, of course. So we also developed an inspection roboter. And now we have another video. I hope this one will work. I will increase a bit for time reasons. So we go inside now. It's an animation, of course. And you see what our roboter is doing. The first topic he is working on is a visual inspection. You can see now there's a camera on top of the roboter. This camera is looking in the inside of the stiffener. And you can see in this case we have a lot of corrosion here. And he can send this out to the engineer who is working with a roboter. The second topic is yes, we would like to find where do we have cracks. So we put negative pressure inside the hollow stiffener, and if you have a negative pressure and a crack, then the air will go through the crack, and you got something like from the tea kettle, no? A high tone. And we have microphones on the roboter. And the last topic is the ultrasonic sensor. So, but before we can use the ultrasonic sensor, we have to clean the steel deck and put away the corrosion products. And then we can, in the second step, we can put the ultrasonic sensor in position, and we can make a measurement of the thickness of the steel plate. Okay. And the second problem is, one problem is corrosion, second problem is the traffic load. In Germany, but I think in nearly all countries, we had 50 years ago only smaller traffic than we have now. We have smaller trucks, and we had also not so many of them. Then it increased, and now we have a lot of traffic everywhere. And the opposite is with the bridges. We built the most of our bridges, not in all parts of Germany, but especially in the western parts. We built 60% of these bridges before 1970. let's say 25, 30% between 70 and 2000, and the last 10% we built in the last 10 years. So the old bridges are not made for the new traffic. That's a problem. So we have a statical problem. And this is also, you could also see in the load specifications we have in Europe. These, I don't want to go too much to details. There are two types of loads. One is the load of the wheel, of one wheel, and the other one is the load we have on a typical 100-meter long bridge with 2 lanes. So it increased in reality and also theoretically in the code. So now how can we now how can we reinforce this hollow stiffener? And there are, of course, only 3 solutions. We can go from below. There we have a problem of accessibility because usually these bridges are going above a river or let's say a railway, and it's not very easy to go there, to put these plates in position. And also the cross beams, as you can see here, are have to be cut away. The space is not enough we have here. The second possibility is to come from top, but there we have the traffic, which has to be stopped. And also the height of the roadway will be modified, which makes a lot of problems with the gradient and several problems. So our idea was put a reinforcement from inside. Inside means that we will put, in this case, a flexible hose, woven fabric impregnated by resin, and with a laminated foil inside the bridge. This will, first of all, will stop that more water and salt will go inside the inliner, the stiffener. And also, if you clean before you put this inliner in, if you clean the steel deck, then you can also stop the corrosion. The second thing is now the statical problem. What we did is that we put high strength carbon fiber inside the hose, and so we have also a reinforcement. So we could have a higher loading capacity of the hollow stiffener. The problem is now, how can you put it inside this inliner? And it's a problem. Now you see I have here a sock. The thing is, outside this, we have a foil. Inside we have the resin because we have to glue it. But you couldn't transport this inside the stiffener when the glue is outside. So you have to make something like an inversion, like I'm doing here with a sock. We have a little animation here. I can show you how it works inside. Now the glue is inside and it's going outside. You have to work with pressure from the right. That's one technique, which is here in this case a bit complicated because our carbon fiber doesn't like it to be inverted. So we also were thinking about a second possibility, and this is a pull-in method. So we have some trolleys. You see the trolley here on the top, and we pull the inliner inside with the trolleys. Then we have a lot of ropes, 2 ropes here and one on the 2 ropes here and one on the bottom. And this bottom rope is fixed by 2 carabiner hooks. And now we remove the bottom rope, so the carabine hooks are going one to the left and one to the right. And so for gravity, the inliner will go down. Then we can remove the trolleys and we can put pressure on the inliner, and then it's in position. And it's not only theoretically, we also did it here. This is a trolley. This is just on the top of our building. We have a test lane, and this is how it looks like. But without the glue, of course, no? And this is now the product. You see the inliner inside the hollow stiffener, and you see also which this was a big problem, the corner here, to get it in this position. But also here, you can see it. I don't know if you can see it, but it works very well. And we made also some mechanical tests. This is a part of a bridge, and this is a mechanical test to simulate the load of a wheel of a truck, and it works quite better than without the inliner. Okay, this was my part, and now Natalie from Butler will continue.
Okay, I will go on for now. I'm going to try to stay within the next few minutes, so we have some time to answer some questions afterwards, maybe get into a small discussion. Let's see what will be possible. Okay, so basically what I'm going to be telling you is all about my bachelor thesis, which was about the sustainability analysis of what Professor Latz was just talking about, this research project of the inliners pushing them in. So we had an application, we had a project, this bridge, as you can see here in the on the PowerPoint. You can see the cross-section down below. The cross-section drawing, you can see the Autotopic cross-section of the bridge. It was built in the 1970s, so it's pretty old. It was built according to old loads. We have heavier trucks and more trucks nowadays. Yeah, this is a bridge you can find in northern Germany, somewhere in Schleswig-Holstein. Yeah, if you want to go by, it's called the Plönersee, Kleiner Plönersee. So the question was basically if it is sustainable to apply this research project, which is, the abbreviation is called TOFI, so fiber reinforced inliners, to refurbish the bridge, or if it would be more sustainable to reconstruct the bridge. So you had to take into account a lot of different variables in this whole analysis, and we had to take some assumptions, of course, to make it simple for it to work for a thesis. Otherwise, it would have been too much, of course. So I'm going to just take you through what I did back then as a first idea of how you can go about sustainability analysis when you talk about civil engineering structures, because there are a lot of different methods to derive sustainability of buildings, but there are not so many about civil engineering structures such as bridges. Therefore, I had to basically come up with my own little structure and system to compare this. So I started at the beginning, what does sustainability mean? And the basis back then, I think nowadays it's a bit more nuanced. But when I was doing my bachelor thesis, mainly what I found was this definition of sustainability as the three columns: economy, ecology, and social impact of what you're doing. So if all three factors, the environmental impact, the economic impact, and the social impact are equally distributed, you can call it a sustainable solution. So that's why I decided to say, I'm gonna give each of these different factors 100 points, and I'm gonna see how much points each of the two variants is gonna get. So one time, how much the new bridge is gonna get in the environmental impact factor, how much the research project is gonna get in the other one. Okay, I hope that's clear till now. So what you have to do now, or what I did then, is, well, think about the ecological impact first. What does it mean to assess the ecological impact of a building like a bridge? So basically what you do, also what you can find a lot in literature, is the life cycle assessment. So you look at the whole life of the building, of the product that you're looking at, and see what kind of emissions do you have throughout the different phases of this product. So you have, when looking at this bridge, you have the preparation of the construction site. So basically, if you want to talk about building a new bridge, you will be talking about first demolishing the old bridge. Or if you want to put the inliners of the research project, you have to clean the bridge first. Then you have the production, where you have to use different resources. You have to mold the steel. You have to make the resin of the inliners and the materials that you're using there. Then, of course, these products have to be transported to the construction site. You have to construct the whole thing. Then you have the whole phase, which is, of course, the longest of the use. Then you have to demolish the bridge again, because at some point it will not be able to be used anymore. And after demolition, you have to dispose of it or recycle it if possible. To find out what kind of material I would need, I did a structural analysis of the bridge. First, according to the old code of the 1970s, and then according to the new code. For the engineers on you, I'm just going to quickly explain. So basically, I took the moments of under the old code, compared it to the moments I got for the bridge, the maximum moments of the new code, and saw what the increase is. So the increase between the moments means that I need more steel to still be within the limit states of the what is necessary to carry the loads. So the increase of the loads means more steel in the bridge, in the cross section of the bridge. So what I calculated was that now, or under the old code, the bridge would be around 489 tons, and the new bridge should have 752 tons of steel, because it's a pure steel structure. And that's just what I looked at. I didn't look at more anything that's like around that, because we, as I said, we had to simplify it. Then we had, I went through all of the phases. And first, of course, I distributed the points, which I had said were for every part 100 in the beginning. So as you can see here, it's 100 in total for the that you can get for the ecological impact part. Then I decided to give each phase the different points. So the preparation gets 15 points, production 30, transportation 10, construction 30 again, disposal and recycling 15 points. So preparation of the construction site, as I said already, for the research project, you just have to clean it. So you have basically very low ecological impact. For the new bridge, you have high impact because you have to demolish the old bridge. So that's why the new bridge doesn't get any points in that part. And the research project got full points. The production, new bridge has to be built out of steel. You could maybe think of using the steel of like recycled steel, if that's possible, if it has the same quality. But for the research project, in the production, you only have to create these inliners. So you don't have to create like the whole bridge. So working with steel is a very difficult topic nowadays, especially when talking about sustainability, because steel has a very, very high impact on the environment, because it's very it's very costly to first mine it and then to change it, because you need high energies, very strong CO2 emissions through that, and people are trying to find ways to make steel carbon neutral, which is going to be very interesting in the future, definitely. But for now, that's not happening, so we still have to work with the old, with what we have for now. Transportation, well, there you can see the new bridge. Well, it has to, all these parts have to be transported. It's going to be huge. You need a lot of trucks or trains, whatever you're going to use to transport it. For the research project, you have to transport it, yes, so you miss a point, because you're going to have emissions through that, but you don't have to, it's not a lot. It's just like these inliners for the few hollow sections that you have to fill. Then, of course, the construction part. Constructing the new bridge has high emissions, so you will have the machines that are going to be used as the welding, which is producing emissions. And in the research project, of course, you don't have that much. Then disposal and recycling. We have to consider that you can recycle steel. So that's the very good part here, because it's a pure steel bridge. You can use it. often also, if do it in a good way, maybe even with the same quality as before, so you don't even have to downcycle, but you can recycle actually. Then the research project, you lose the material of the inliners, because when you melt, you can't take it away or reuse it from using it in the cross section anymore. But you have to basically melt the steel down, and in the process, the inliners will burn up, which is good because then you can still use the steel afterwards, but you cannot use the inliners again, so you lose material. So in the end, you can see that in the ecological impact, the new bridge loses very strongly, and the research project basically gains 90 points. You will notice that I didn't talk about the use or demolition part. Those are the same emissions that will happen for the new bridge or the research project, so I didn't take them into account because they would be the same. Okay, I will try to keep the rest a bit shorter. Life cycle costs is basically what you have to take into account when you do the economic impact assessment. So, as I said, it's an equal thing. It's an equal column of the sustainability analysis. It goes in with 1/3 as everything else. And here I used formulas that I found to assess the costs. I used the costs over the whole life cycle, of course, because you have to. This was the difficult part, to kind of say for which time am I going to look at this. For only like the usage time itself, am I going to look for 100 years and take this as a basis? It's not that easy, because also with the bridge, with the research project, is has a lifetime of 30 years. And the new bridge, if you build it new, will have a lifetime of around 100 years. If it, of course, the loads don't go up, and if it's maintained properly and everything else. We're talking about optimums here. Then I calculated it with on the basis of some information, and decided to give the most sustainable solution, or the more economical solution, the research project, 100% as a basis, give it 100 points, and then deduct the points that the other one is more costly to from the 100 points. So that's why the new bridge would get 90 points, because it's 10% per year more costly. But as I said, I had to have a basis to look at this. That's why I took an evaluation per year, because we have so many different factors, life length and everything. And I didn't look in the past. I only looked like from now, if you implement it now till when it lives. And then, of course, I didn't take into account, like with the research project, if you would, after 30 years, have to build a new bridge or anything. So I just looked in this time per year, how much it would cost. So there are definitely some points where you can say this still could be worked on. But again, it's just a thesis. Then last point, social impact. So this is not so easy to put into numbers, to quantify. Then especially thinking about what is the social impact of a bridge, of building a bridge or constructing a bridge. Basically, the definition of the social impact factor is the impact on the health, comfort, and well-being of the users. So that mainly means that you have noise during the construction, for example, you have traffic impediments, and what I took as a big factor is the duration of how long this noise or the traffic impediment is keeping on. Because just imagine you hear very loud, very aggressive noise, but it's very short. You won't be as annoyed as you have like soft noise, which is just always constantly in the background. That's why I gave duration a very big part here. So then I decided, okay, the noise for the new bridge is going to be pretty high because you're working with steel. So it loses a lot of points in the research project. Well, there's going to be some noise, but almost none, basically implementing the inliners. Then traffic, of course, the new bridge. If you construct a new bridge, you have to completely cut this traffic line. The people have to deviate, so it's a huge impact. Research project, well, maybe you have to cut it for like a few hours or something, but there's almost no impact there. And the duration, of course, constructing a new bridge takes time, especially if you have to demolish the old one before. then the research project itself doesn't take that long. It takes a bit of time, but will be done in less time than constructing a new bridge. So coming to the end, if you look at all these three different columns that make up sustainability according to literature, then you see that definitely the research project won in the points that I have that I gave the different things. I just want to say again, for the ecologic part, I took data from a website that's called Ökobaudat, where it's a database where the German government works together with different parts. I don't know which institutes, but they will basically put up a database so you can see what impact does which material have, or which transportation thing you're using, so that you can compare different materials or things basically that you need during construction to and their ecological impact. So they take into account things, for example, of just have to look for where I wrote it down, like water usage, waste, resources, ozone damage potential to further global warming in CO2 kilogram equivalents, and so these kind of things, and then you can just see how much impact it actually has. So I think this was a good point to get the ecologic data from, and I think maybe that was interesting to you. So just to sum it up, we can say the most sustainable part was the research project. Then problems I was encountering was definitely missing data. So this database still doesn't have enough information about all the different construction materials or things that you have during construction period. We still have to definitely work on that, and there are no or very vague guidelines on how to find out what is sustainable for civil engineering structures that are not buildings. And then, so too few rating systems in especially that part is important. And then I just put my email down there. So right now I'm at the Bauhaus-Universität Weimar, but this bachelor thesis I wrote it with Professor Latz here in the University of Wismar. But yeah, if you have any questions, you can also just drop me a mail.
Können wir nochmal nach oben gehen, dann können Sie beide E-Mail-Adressen sehen, falls jemand eine Frage hat. Ne? Ganz oben. Okay, two final sentences. Our job was to use buildings for a longer time and to avoid the new construction. So this is also for Weimar and Wismar. We need young students and engineers with fresh ideas to use resources more effectively in future. So this is what we would like to tell you. No? So wherever you are coming from, you're invited to visit our engineer programs in both the towns. So, and if you have questions, and now I will change, we have to change again to the chat. There was one question, for me, not completely understood everything, but one thing I can say, I think all of you can see the question. Yes, the foundation must be reinforced. Okay, just the tuned mass damper means that you have an addition, let's say 1% of the total mass. This is enough. In our case, it was even less, no, with the water. This tower has 500 kilo of steel and a lot of other things on top, and we have not very much water inside. No? So this is a very effective problem, and for the foundation, it's nothing. You don't have to work it's the other way around. If you put more steel in the construction to make it stronger, then you have to add 10% of the total mass, for example. But with the tuned mass damper, you can do it with much less weight. I hope I understood your question in the right way. But if you have other questions, either in the chat or also with a microphone, no problem. We will try to answer them.
And also you can see our emails here, so just feel free to drop us an email.
Yes, hello.
Yeah, hello.
Yes, I asked a question, and I would reply to you that we can distribute the weight along the whole area of the bridge by some lighter materials maybe, and it will provide some friction for the vertical movement of the water.
Oh, the water doesn't work for the bridge, by the way. No? The water works for horizontal vibrations. So putting water on the bridge only if you have a bridge which is, I showed one photo of one bridge. If a bridge is very slim in horizontal direction, which is not very often the problem. This bridge was vibrating in horizontal direction. Usually for bridges, we are doing this, what I showed in the beginning, since 40, 50 years. It's a very common system all over the world, I think now. If you have a bridge with a resonance problem, you put the mass inside with a damper in the springs. There are a lot of companies, for example, in Germany, you have two companies who are producing such tuned mass dampers. It's called Maurer and Gerb. And for bridges, it's not a big problem. Water works only for horizontal, because water is sloshing horizontally direction. It works only for almost for towers.
I understand, but I'm also thinking about like champering the down of the bridge, like making chambers, like for example, the trucks of the trucks of petroleum materials. You know, they are chambered. So the water does not really get it move freely, really, and we can also hang some hang some like some material, steel or whatever, to also like reduce the damping of water itself by friction in some design. I'm not like it's an abstract idea. I'm just conveying my abstract ideas.
So you're basically talking about having the water damper and putting like something in there to reduce the friction
chambers.
of the water.
Yes.
This is okay. Yes, now I understand. This is also a possibility, but the problem is it's difficult to. At least you got a turbulent movement of the water, and these systems are difficult to get the exact damping ratio you need. Okay, I couldn't talk about everything we are doing. We have now another screw, let's say, where we can just really get, let's say, 9.5% of damping. And with the other method, I know this, it's quite difficult. At least you need this linear sloshing, and you got some turbulent movement of the water, and then it's getting a bit more complicated, as far as I know. And as far as I know, these research projects. For example, one of the skyscrapers you have seen in my presentation, it was that one on the right side in San Francisco, who is using something like this. For example, if you have a wind turbine, this wind turbine can vibrate in every direction. And you can also only put these, let's say, bulkheads only in one direction. And it's difficult to do it for a circular vibrating system, as far as I know.
Okay, but I think like we can like work out these problems in multiple ways.
Yeah, of course.
Yes.
Mm-hmm. Yeah, for sure. Mm-hmm.
Okay, thank you.
Thank you very much. Are there some more questions?
I see somebody's typing.
Yeah.
Wait for this.
Yeah. So we have 1 or 2 minutes left. If somebody has some more questions, of course, you can send us an email, and then we can either meet in a video conference or we can answer with an email. Ah, yes. Okay. That's true. That's a problem with our tower we just built here. Another case of instability. It is, as I just told you about the bridge, it is not very much water. Instability, of course, was a problem with our tower because we would like to have a system which we can easily get into vibration. That means it has to be very slim, and if it's very slim, we can also have static instability problems, buckling, and so on. Yes, this is at least the trick with the tuned mass damper, or also the tuned pellet damper, is that he eliminates the dynamic problem, and you need only a bit of water, so you don't get too much heavy loads in the tower, so that you get new problems with other for other reasons, instability, for example. I know it's difficult to describe such a problem on one hand for engineers, on the other hand for somebody who is studying something else, but we tried our very best. Okay, no more questions, so we are just in time. Then we would like to say thank you very much. Hope we can meet one of you somewhere, somehow. Yes. Thank you very much.